folks, we're back. Hopefully the picture is a little bit better for you. I've made another adjustment hoping that this picture quality gets better and better. So we're working on it. Okay, so we're going to learn about something called scientific notation. And as I've indicated before, as we saw when we looked at the concept of a mole, science in general deals often with huge ranges of numbers. Very, very, very tiny numbers or very, very, very big numbers. And so if you're using a decimal point and zeros, just completely unusable at some point. You saw when you tried to draw a mole how hard that was. So in that case, of course, you can just say 1 mole. But nonetheless, we need there needs to be some way of dealing with big numbers or very, very small numbers conveniently, so that we can concentrate on the calculation that we got to do. And what we're going to learn about is something called scientific notation. And basically, the principle is you're going to come up with, you're going to turn any number using scientific notation. You can turn any number into 1-digit, decimal point, and then a couple other digits, okay? Any number. I don't care if it's a billion, zillion. I don't care if it's 1/20th of a trillion or whatever. It will be, you can turn it into having 1 digit, then a decimal place, and then some digits, okay, so that you can deal with that math. How are you going to do that? Well, you're going to express that number as, you know, a single digit and a decimal place and then some other digits times either 10 to a big number, okay? Essentially, you're going to have another component here that tells you what is the magnitude of this number, okay? Should that decimal place really be like, you know, 100 zeros that way or 100 zeros that way? You'll have another component to it, a 10 thing that tells you where that decimal place really ought to be if you weren't converting it into this convenient system. Okay, so that's scientific notation. I didn't do the best job of explaining that off the cuff, so to speak, but let me show you here. Okay, so this is scientific notation. Okay. All right, and so in general, the general idea of it, it is a, I'm writing too big here, it is a trick to deal with very large or very small numbers. Okay. All right, and so here's sort of an intro to how you achieve this, sort of building it up gradually, the process of it. So if you had the number 523, you could write 523 as 52.3 times 10. Those are equivalent, right? Those equal each other. Okay? Anytime you multiply by 10, you just move the decimal place 1 place to the right. Okay? Could also express it as 5.23 times 10, or times 100. Okay? And that is also equivalent. Those two things, those expressions, you can put an equal sign there, right? So you move that decimal place 2 places to the right. Okay? Well, we can also change how we express this 100. Okay? So that equals 5.23 times 10 to the 2. Okay? And that's, maybe you could describe that as sort of the key jump in logic here, that the 2 is essentially telling you how many decimal places this thing needs to move. Okay? And so for it to convert it back to the the real way of expressing it. Okay. Okay. And so that's the general form of scientific notation. Okay. All right. Okay, so let's do a little bit of work going back and forth between, kind of the normal way of expressing a number and scientific notation. Okay, so to convert 7.34 times 10 to the 5th to normal numbers, okay? You move the decimal 5 places to the right. Okay, so that would actually turn into 734,000. Okay. All right. Now, what if it's a very, very tiny number? It's a number with a whole bunch of zeros in front of the digits. So decimal place, bunch of zeros, and then an actual number, okay, or actual digits. Well, you can express it the same way. You just use a negative number on the exponent to the 10. Okay. All right. So. Same for negative exponents. Okay. But opposite direction. Okay. So E 7.34 times 10 to the negative 4 actually equals 0.0. So we move that 2 places, or 4 places, 0.074. Okay? Okay. Now, you need to be comfortable. These different colors are working out okay. I know it didn't very well with the other camera, but hopefully this camera will show it better. If not, then I will stop using it. So I just want to say, must be comfortable. Converting back and forth. Okay. All right. So instead of 1, what do I have here? 1,452 grams. Okay. You could express that as 1.4 1.452 times 10 to the 3 grams. Okay, so there's an unwritten decimal place right there, right? And so what I've done is, because you could say that the goal a lot of the time is to have one digit to the left of the decimal place, and then whatever other digits you have to the level of your accuracy to the other side. Okay. So in order to get the decimal place from over here so that there's only one digit to the left, I got to move the digit 3 spaces. Okay, thus 10 to the 3. Okay? All right. Oh, where's my, okay. Okay. So in addition to being able to use scientific notation, another thing sometimes we do to express a very large number, or to conveniently handle very large numbers or very small numbers, is we use prefixes. Okay. So like rather than gram, kilogram. Okay. If it's 12,000 grams, okay, then it's 12 kilograms. Okay. So very, very convenient. Another shortcut for very large numbers or small is prefixes. Okay. And you can combine them as well, okay? You could be using scientific notation and prefixes. They're not exclusive to each other. All right, so section prefixes. Okay. So for instance, kilo means 10 to the 3. Okay. So that's the 3 dots international sign for therefore. Therefore, 1.452 grams, or I'm sorry, times 10 to the 3 grams, okay, is the same as 1.452 kilograms. Okay. All right, and there are other ones. Milli are some of the ones that you might be familiar with. Centi, yeah. Okay, and these are something that you really kind of want to commit to memory. Okay, so prefix, abbreviation. And associated exponent. Okay. All right. So there's nano, and that is a lowercase n, and that is 10 to the negative 9. Okay. So if you said you had 10 nanograms of some compound or something like that, then what that actually means is 10 times 10 to the negative 9 grams. Okay. Micro, and I'm forgetting what that Greek letter is right now. 10 to the negative 6. Milli. M and that's 10 to the negative 3. And centi. Okay, that's C. It's 10 to the negative 2. Okay. Deci, that's lowercase d, 10 to the negative 1. Okay. And then the positive ones that I have on my chart for you to commit to memory is kilo. Okay, that's K, 10 to the 3. And then mega. Capital M, and that's 10 to the 6. So I guess you could say, I've never actually even thought about it, we tend to use prefixes more commonly with small numbers, things that are less than whatever unit it is that we're dealing with, okay? Rather than, we only have these two that are positive exponents, so things that are bigger than the unit you're using. Kilogram, kilometer, all those kinds of things. Okay. Okay, so we now know how to convert numbers that are in scientific notation to normal numbers, or normal numbers to scientific notation and stuff. But now we need to be able to do operations with them. Okay, how do you handle that times 10 to the, if you're doing an addition problem or a multiplication problem or whatever. It's actually pretty straightforward. So for multiplication, okay, if you're multiplying two scientific notation numbers, 10 to the whatever, something 10 to the whatever, another one 10 times to the whatever. If you're multiplying those two things, you're going to multiply the digit numbers, okay, and then you're going to add the exponents of the 10, okay, and the product, the answer will have the times 10 to the whatever was the sum of those two exponents, okay. If you're dividing, then you're simply going to subtract those two exponents. Again, you'll do the math between the two digits, okay? But then how do you handle the 10 to the whatever? Well, you take the, you take the numerator exponent minus the denominator exponent. And that, whatever that gives you is your product exponent, okay? Or I guess it would be quotient exponent. All right, so that's how you handle multiplication and division. When you're adding two numbers that are in scientific notation or subtracting, what you have to do is you have to you look at how many digits they have to the right. Let's see. I want to express this correctly. Okay.
I am hungry.
Okay, folks. Unexpected break there. So that's how you handle multiplication and division. How do you handle doing addition and subtraction when your numbers are expressed in scientific notation? How do you deal with the 10 times some exponent part? Well, the 10 times some exponent part has to have the same exponent. Okay, so what you have to do, if you're adding two numbers that are expressed in scientific notation, you have to change one of them so that the exponents match. Okay, and same for subtraction. Okay, so that's how you handle those operations. Let's go back and put it on the board, and so that you can see what I'm talking about. All right. Okay, so oops. Let's see. Doing multiplication subtraction, division, kind of a strange order here, and addition. With scientific notation. All right, so first multiplication. Okay. Simply multiply the digits. Okay. Then add the exponents. Okay. All right, so example here. Suppose we had, suppose we have this number, 3.45 times 10 to the negative 3, okay, times 2.78 times 10 to the 6, okay. That is going to equal, if you multiply 3.45 times 2.78, what you're going to get is 9.59, okay? And then you simply add those two exponents. So negative 3 plus 6 is 3. Okay. And then for division, it's the same thing, except you subtract that exponent from that exponent. Okay. All right, so division, you divide the digits, then subtract exponents. So, are these the same numbers? Yeah, they're the same numbers. 3.45 times 10 to the negative 3. Okay. Divided by 2.78 times 10 to the 6. Okay. So that 3.45 divided by 2.78, that is going to give you 1.24, okay, times 10, and then what you're looking at for this exponent is going to be negative 3 minus 6, okay, which is going to give you 1.24 times 10 to the negative 9, okay. And I want to take this moment to teach you about a really important habit that you want to get into when you're doing calculations, okay? And that is, you want to have a double check in your mind, does this make sense, okay? We can sometimes know exactly what we're doing and we make one small mistake, okay, and the number, we get the wrong answer. Okay, where if we adjusted, wait a minute, does this make sense? We might be able to catch that and then correct it. Okay, so what I mean for that is, does this number make sense? Well, that's a tiny number. Okay, 10 to the negative 9 means we need to send that decimal place 9 spots that way. So 0, 0, 0, 0, 0 right in front of here. Okay, so move this 1 and then make 8 zeros and then dot. Okay, so it's a tiny number. Does it make sense that we get a tiny number? Yes. We took a small number, okay, so if we were going to write this out, that would be 0.00345 divided by a huge number, okay? So a small number divided by a huge number is going to give you a very tiny number, okay? You always want to do that when you're doing, it's a great thing to do when you're taking your test and stuff, because it'll stop you from making careless errors sometimes. Okay. So let me do addition and subtraction. I already told you about it, but let me do it real quick for you. Okay. I might as well get this part too. that trick of, does it make sense? Doing that check. It's something I always tell students, and some adopt it and some kind of goes in one ear and out the other, and it, you can see it on an exam sometime where just like, oh, if you just thought about it in terms of that rather than just sort of robotically plugging in the numbers, then I bet you would have caught this guy. I don't have to use so much red pen. Okay, all right. So that's division. Addition. Okay, and for addition, let's first convert the numbers have same exponent. It's not the greatest sentence, but especially since I've already explained it to you, you get an idea of what I mean. Okay. All right. So let's say we have this guy, these two guys, 2.32 times 10 to the negative 3. Okay, plus 8.65. times 10 to the negative 5. Okay? All right, so what we want to first do is pick one of these and convert it so that either they're both 10 to the negative 5 or they're both 10 to the negative 3. Okay, it looks like in my notes I convert this one to 10 to the negative 5. Okay, so how do I do that? If I want to make that 10 to the negative 5, when I'm making the number this part smaller, right? So I need to make this part bigger, all right? So that I don't change the number, okay? I just want to convert the format. I don't want to change the actual number, all right? So what I'll do is I can change that to negative 5 if I move that guy over 2 spots, okay? So that's going to be 232 times 10 to the negative 5. Okay. Might be worth your while if that seems a little bit confusing. Convince yourself right now. Pause the video and convince yourself by. Oops, I should put the decimal place there. By moving the decimal place, right? So 10 to the negative 5 means that it'll move 5 spots over there. So 0.00232. Okay, and for this one, you move it over 3. 1, 2, 3. So 232. Okay, so they're the same numbers. Haven't changed the value of numbers, just changed how they're expressed. Okay, and once you do that, then it's easy. All you have to do is add these two numbers, and it's your answer is going to have the 10 to the negative 5 multiplier. Okay, so so you can bring that guy down now, and that's 8.65 times 10 to the negative 5. Okay, and so that ends up, if you add these two numbers, that's going to be 240.65 times 10 to the negative 5. Okay. Now, it turns out, because of something called significant figures, which is going to be, I think, our next subject here, it's not actually fair of us to count all those digits. So we actually need to round this to the nearest ones place. Okay, since that's a 6, we'll round it to 241. Okay, so 241 times 10 to the negative 5. Okay, and that's our correct answer. I'll explain significant figures in just a second. Okay, so subtraction. All right. Must first convert same exponent. Okay, and then you can do the problem. Right, so here. Okay. 5.467 is 10 to the 3 minus 42 and 3 times 10 to the 2. Okay, so you can convert either of those, but they need to be the same. So I'm going to convert this guy to 10 to the 3. Okay, so if I'm making this bigger, this is going to go from 100 to 1,000, and I got to make that smaller, or I've changed the value. Okay, so I'm increasing this by 1 exponent unit, so I need to decrease that by 1 decimal place. Okay, so 4.23 times 10 to the 3. Now they're the same, okay, and I can simply add those two numbers, okay, and I'm going to get, oh, I'm sorry, darn it, subtract. Here, I'm going to write it out nicely. 5.467 times 10 to the 3, okay, minus 4.23 times 10 to the 3, okay, and that's going to give you 1.24 times 10 to the 3. Again, cut off part of that, rounded part of that because of significant figures. Okay. All right. So before we get in exactly to significant figures, we're going to do a related topic, and that's how is this described? The quality of measurements. Okay, how well do we know a particular number? For instance, when we're weighing something, we're limited by the scale or the balance that we're using. Okay, and you can take in some sort of a number from some sort of data, like a weight or something, and then do calculations with it. But the calculations you do with it have to sort of maintain that level of accuracy. And what okay, so that's the basic concept between significant figures. I'm getting ahead of myself again. We first want to sort of look at our language that we use in terms of accuracy. You know, how accurately do we know a weight, and how precise do we know something? And it turns out we use those two interchangeably, sort of in everyday life, accuracy and precision. But they mean different things. Okay. And so, I want to teach you the difference between them so that you know it. And then, we still use them pretty interchangeably in society. I have to catch I teach the idea, and I have to catch myself not interchanging them and stuff. But essentially, it's funny because this class often has a lot of military students in it. And if you've been in the military and you've done any sort of range shooting, you probably already know this definition, okay? So accuracy is how close are you to the real number, okay? Whereas precision indicates how reproducible, if you do multiple measurements, how close are they going to be? Or are they just sort of all over the place, okay? All right, so let me put some words here to all that. Okay, so I think I'm on Roman numeral 6. I might be one off on that. I pray I'm not. Equality of measurements. Precision versus accuracy. Okay. Accurate? That is, how close are you to the real value? Okay. Precise? How reproducible your measurements are. And then for you military folks, if you're like, oh, I haven't really thought about that. As soon as I show my perfect example for this, you'll be like, oh yeah, actually I did know the difference between those two. And you can do that by showing targets. Okay. Let me do 3 of them. Didn't mean to be this big. Let's see if I can fit one there. Sort of cartoon. Okay, so let's say we're shooting at these targets here, yeah, and we're like this. Okay, then we might conclude from that, in this situation here, that we are very precise. Okay, but we weren't very close to the target. To the in science, we'd be thinking about the actual value. Okay, very precise, low accuracy. Okay. You could have something like this. Okay. There, you're actually closer to the real value, but your reproducibility is a little bit lower. Okay, so this is, I'm using arrows all of a sudden, sorry about that. High accuracy, relatively speaking. Okay, but low precision. Okay, and then you could be all over the place. The one time in my life I shot an actual rifle. Yeah. All over there. It's a good thing I'm a vegetarian. I could never hunt for my food. Okay, so this is low both. Okay? All right. Okay, finally, we move on to significant figures. Okay? And the idea behind significant figures is, you know, let's say you measure something. You measure, I don't know. Let's say I measure the length of this room by walking it off with my feet. Okay, that's a pretty inaccurate way of doing it. I'm probably going to come up with the right number to the right feet. Yeah. So if I pace it off and stuff, chances are I'll get something like that. So what do I think this is? I think this is probably somewhere around 40 feet. If I paced it off, maybe I'd come up with 38. Probably be 38 plus or minus 1. Okay. My shoes and stuff, yeah, it's probably about 12 inches. So plus or minus 1. All right. Now, let's say I wanted to, for some reason, I wanted to do that, and then I wanted to do some division. Maybe I want to put something in here, and I want to make sure the right number fits and all that stuff. So I divide. I take that 38, and I divide it by some number and plug it into my calculator. My calculator spits out something like 12.695342560. Okay, as calculators will do. I forget what that is in math. If it doesn't just stop on it. Anyway, it may be infinite. It may just go on and on, like pi, or it may actually stop. But it may stop just because of the mechanics of doing division. Okay, and it may give you 10 digits. Okay. Now suddenly we say, let's say we were trying to fit in desks. Oh, we can fit in, that many. That's not a good example, but nonetheless, that answer that I come up with implies that I know the length of this room a lot more accurately than I actually do. Okay, I've taken a very, inaccurate, probably also low precision type of measurement, and now I've sort of represented it as though we know it really, really well. That is the main concept behind significant figures. Okay, in most of the measurements we do in science, we assume that the last digit, when we're writing a mass or we're writing a volume or something, the last digit we put up there is the one we have the least confidence in. Okay, that's our most uncertain number. Okay, and the general concept is that calculations that use that can't your answer can only be as detailed. Sorry, I'm blanking on a word here. As your least known number. Okay. All right. Sorry, I'll bundle that up at the end. But I've got plenty of writing here to do for you, which will clarify everything. All right. So this is B. Significant figures. Okay. And this is a concept, by the way, a lot of us scientists and chemists and stuff like that are kind of sticklers on. I'm definitely a stickler on this, so make sure you appreciate this and stuff, and because I don't want to have to ding you for it. Okay, so. Say we want to calculate the density of a person. All right. They weigh, what do I got? 150.5 lbs. Okay. Now we need to know what volume a person is. How do you think you would figure out the volume of a person? Okay. Treat them like a rectangle and stuff like that. It's not going to be very accurate. Okay. So you could do liquid displacement. So you put them, if you had, I don't know what kind of thing you have, some type of bathtub with markings on it that tell you the different volumes, and you have it full of water. You submerge the person in there quickly and read your value, and you see how much water was displaced, and that tells you what the volume is of that person. Okay. All right, so volume of water displaced. Okay, that we come up with 5.3 liters. Okay, so our this last value is is probably plus or minus 0.1. Okay. All right, so do the division. So you've got 150.5 divided by 5.3. This is LBS. Okay, and this is liters. Right. And our answer that we read off our calculator is going to be 28.36 or 396, sorry, 396.22641 lbs per liter. Okay. This shows you what I mean. Now if we go and say, oh, you know, my buddy Mike, would you like to know his density? Well, his density happens to be 28.96220 pounds per liter. Oh, wow, you really know Mike's density. Okay? No, this misrepresents how well we know Mike's density. Okay? In reality, when we start using the rules of significant figures, we know Mike's density is 28. That's as far as we can legally claim we know his density. And I'll explain how that is, or you know, how I come up with that specific cutoff. Okay. All right. Okay. So I have written in my notes here. Do we know? I don't have it written here as Mike's, but I decided to go with Mike's. Accuracy? Question mark, question mark? No. Okay. All right. So, continuation of that, actually let me put it down here. The volume measurement limits our accuracy. Okay? The accuracy of our final answer is only as extreme as our least accurate measurement. Okay? You always assume that there is uncertainty in the last digit. There's uncertainty here, there was uncertainty there. Hi folks. Okay, so talking about uncertainty in measurement, and if you've been following strict guidelines, so forth and so on, it's assumed that if you give somebody a measurement that there is uncertainty in the very last digit, and that's the only place where there's uncertainty. So on a balance, or a scale, if you're weighing something, typically that last digit that's on the balance, there's uncertainty in that value. Okay? And a similar concept is when you are using something with grid lines, a ruler, in lab if you're using a burette or a graduated pipette, so forth and so on. There's uncertainty in the last value you give there. Now where does that last value come from? Okay, so let me just reiterate. Uncertainty in last digit. Okay. So if you were reading, a burette is a very common one, and if you're taking the lab class, you'll be watching me do that a lot. And so there's like, say, your main striations. Let's call this 10, and then this is 20, and this is milliliters. Okay, and then let's see if I can figure this out correctly. Probably not. Well, okay, that would be 5. And so 1, 2. I knew I was going to blow it. So 1, 2, 3, 4, 6, 7, 8, 9. Okay. And so you've got you've got some value of solution in here, and you've got some meniscus like that that's going through. when there are grid lines or divisions, however you want to say it, on some instrument that you're using to measure, such as a burette, what you should do, best practice is to estimate in between the smallest grid lines. Okay, so this would be 10, 11, 12, 13, 14, 15, 16, and then, this can get pretty hard, especially if you have old eyes like myself. But I would say that is maybe just a little bit past the midpoint. In a meniscus, you always look at the lowest point, okay? And that's just probably past the halfway mark between 16 and 17, okay? So I would call that, with my eyes, 16.6 milliliters, okay? Again, there's uncertainty in here, but point being, with the burette, you want to be sure that you get that extra digit there, okay? That you don't just call it 16 mils, okay? All right. Okay, so I've introduced the idea of significant figures. So how do we operate with significant figures? Well, the very first thing you have to be able to do is you have to be able to look at a measurement or a value given and decide how many significant figures are in that measurement before you can manipulate it and do any operations, put it into your calculator or whatever the case may be. Okay. And so there are some rules about looking at a figure and deciding how many significant figures there are. Okay. In general, you start from the leftmost and you come here, and then any non-zero digit is significant. Okay. And then you have zeros, any zeros in between non-zero digits, those are obviously significant, okay? Trailing zeros, if there's a decimal place, are significant. So if you had 2,500 0.0, okay? That would be, what is that? 2,000. That would be 5 significant figures. So zeros after the non-zero digit are significant, okay? Zeros that are in front, sometimes referred to as leading zeros, are not significant. They're just placeholders to tell you just the magnitude of this number. Okay, so let me reiterate that with some text on the board here. Okay, so the first task in dealing with significant figures, look at a value or measurement and decide how many significant figures it has. Okay? I'm going to refer to this from now on, probably in the course, as sig figs. That's a common abbreviation. Okay? All right, so one, determining how many sig figs in a given number. Okay. I'm going to place this pen here. Okay. All right. So as I said, you read left to right. Okay. Counting sig figs. Okay, so left to right, the first non-zero digit you get to, you count as a sig fig. Counting sig figs from first non-zero digit. Okay. All right. Some sub-rules. All non-zero, this is kind of obvious, I think, non-zero digits are significant. Okay. So 613. 1, 2, 3, 4, 5, 6. Okay, or I shouldn't say it that way. 123,456. Okay. This 3 sig figs. Okay. 6 sig figs. Okay? Easy. And as I mentioned, numbers in between, or I'm sorry, zeros in between non-zero digits are significant. Board's a little bit wet there. 0 located in between non-zero digits are sig. Okay. So 5004, 602, 6. Let me count these here. Okay, 6, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and that 2. Okay. All significant, significant, significant. Okay, so 4 SFs, sig figs, 3 SFs, 16 SFs. Okay. All right. Now the trailing zeros, the zeros to the right of your non-zero digits. Okay. Quote, trailing zeros. Those at the end are sig. Significant. As long as there's a decimal place, decimal point included. These are conventions. These are things that are agreed upon in the science world. Okay, as long as there is a decimal point included. Okay. Otherwise, they, and by they I mean trailing zeros, don't count. Okay, so 5.640, 12, 0, 0, 0, point, okay, or 12, 0, 0, 0, 0, no point. Okay, Okay, so this would be 4 SFs, 4 sig figs. Okay, this is 6 SFs. Okay, and this is 2 SFs. Okay. All right. And then leading zeros is the last thing we need to do to describe how you look at a number and decide how many significant figures are in it. And after we can identify how many sig figs are in a given measurement or a given value, then we're going to talk about, well, how do you do mathematical operations with those and maintain good significant figure practices. Okay, so leading zeros, those to the left of the non-zero digits. So leading zeros those to the left of non-zero digits. Okay. Insignificant. Non-significant is probably a better way of saying that. Okay. All right. They're just placeholders, again, to give you an idea of the magnitude of the number. Okay. Okay, so how do we handle sig figs in calculations? Okay. It's a little bit like scientific notation. There's sort of one strategy that you do for addition and subtraction, okay, that's similar. And then there's a different strategy that you do for multiplication and division that is similar. All right. In general, when you are doing addition, and by the way, we're going to, I can't remember if right here, we're going to combine scientific notation with sig figs. I think we do. But certainly throughout the course we will. We will be using both. We will be paying attention to good significant figures practices, and we'll be using scientific notation. Okay? And this is all to avoid that kind of problem that I explained last time where, you know, just because your calculator spits out 20 digits doesn't mean that you really know the density of a human being or whatever it is that you've gone out and figured out. It's just that's a mathematical consequence of doing division or whatever the case is. Okay, so in general, let me give you the general idea of how you do it. In general, with addition and subtraction, what's important is when you're adding some numbers is looking at how many digits are to the right of the decimal place. Okay, the overall process about doing operations and doing sig figs is you are limited by the one with the fewest. Okay, when you're talking about addition and subtraction, whatever values that you're adding, the one that has the fewest digits to the right of the decimal place guides how many your answer can have. Okay, if there's 5 digits to the right, 5 digits to the right, and then you've got one value you're adding that only has 2 digits to the right, your final answer can only have 2 digits to the right. Okay, you're only as strong as the weakest value, let's call it. All right, so that's and the same for subtraction. Okay. For division, what you're looking at is you're not worrying about, well, how many are to the right of the decimal place. What you're worrying about is how many are there total. Okay, there's 4 sig figs here. Okay, there's 6 sig figs here. All right, and then you look at the one that has the fewest. Okay, and then your product, when you multiply two things, your product can only have the same number as your factor with the fewest significant figure. So if you were multiplying these, those three values there, okay, your product could have at most 2 significant figures. So you need to round to that second sig fig. Okay. All right. Let me put some text behind all that stuff. Okay. So C, handling sig figs and calculations. Okay. In general, answer in calculations is limited by the least certain measurement. Come on, bird. Okay. I can't remember if I talked about figuring out the density of a person here in lecture, or was that only in lab? I talked someplace about taking the density of a human being, okay? You're going to take the density of me, let's say, okay? Well, to get my mass is easy. You put me on a scale and you figure out how much I weigh, okay? And that scale is likely, especially if you buy a fancy one, that is likely to have at least 1 digit past the decimal place, okay? And you can probably buy really expensive ones that will have 2, okay? Probably 175 pounds or something like that. And so it might be 175.653. So, you know, potentially you would have at least 4 sig figs in that, or you would have, you know, maybe even 5 sig figs. Okay. Now, where do you get the volume of me? Well, you put me in some tank that's got lines on it. Okay, and then you see how much water I displace. Okay, so you read the water on the lines, and you put me in there, and then you read the new line of, you know, how much water I displaced, and then you do the subtraction, and that volume is how much volume I am. But that's me, or somebody else besides me, reading those lines. Okay, and so your measurement of that volume is probably not going to be terribly accurate. Okay. You know, maybe 2 sig figs, okay? So, but if you did that, division, if you said, you know, my mass over that volume and then put it into a calculator and it ended up with 7 digits, it would be a total misrepresentation to report those digits as the density of Gideon, okay? Because you don't know it that well, because you are limited by that volume. Okay, I'm probably beating this to death here, but let's move on. All right, okay, so rules for addition and subtraction. Okay, and the rules are all guided by number of digits to the right of decimal. Okay, from here on out called TRD. Not my best acronym. Okay. All right, so look at numbers being added or subtracted. Okay. identify the one with least digits, TRD. Okay. Answer can only have the same. The same is a little bit vague, but with that arrow, hopefully you know what I'm talking about. It can only have that same number of digits to the right of the decimal place. Okay. All right, so let me do an example real quick for you. Okay, so 7.939 plus 6.26 plus 11.1. Okay. If you just did all that math without thinking about the sig figs, you'd come up with 25.299. Okay. You want to look for the number that has the fewest digits to the right of the decimal place. That's obviously that. Okay, it's got one digit to the right of the decimal place. And so our answer can only have one to the right. So this should be reported as 25.3. Okay? All right, and same rules for doing subtraction. Okay. All right. How about multiplication? Rules for multiplication and division. Okay. And don't have to worry about TRD here. It's all guided by total number of SFs in your values. Okay. So identify of an operation of a where you have a bunch of numbers you're multiplying, or just two numbers that you're multiplying or doing division with. Identify your value with the least total SFs. Okay. Final answer can only have the same as that one with the least. Must have same. Again, a little vague, but either way, I think. Okay. Okay. So real quick. Let's say we are doing a little bit more complex here. 7.24. Okay. Times 115.6. Okay. And that product divided by 1.846. Okay. If you just spit that out of your calculator, what you're going to end up with is 453.382 4. Okay. So now you want to look in your multiplication and your division and see what are the total sig figs they have. So we've got 3 sig figs here, we've got 4 sig figs there, and we've got 4 sig figs there. So that is the one that guides what our final product can have. It can only have 3 sig figs. And notice, by the way, that this exemplifies why this is different from addition and subtraction, because that actually has 2 digits to the right of the decimal places. That one only has 1, so if this were an addition problem, then that would actually guide how you coalesce these significant figures. But because this is multiplication, we just go by what's the total number of sig figs. Okay? All right, last thing I want to talk about with doing operations in sig figs is exact numbers. Okay? And students actually have a little bit of trouble with this sometimes. They're so good, I'm a stickler about sig figs and I make such a point about it and stuff that they apply it sometimes in places where it shouldn't be applied. An exact number isn't a number where there's no uncertainty. Okay? Well, you may be like, there's always limits, measurements and stuff like that. Well, imagine, I think it's the same example I have in the notes, but imagine I was trying to figure out the average weight of the people in a classroom, okay? And there was 20 people in the classroom and I add up all their weights and stuff. I can add up all their weights and I'll probably, again, know all those weights to something like 4 significant figures, okay? And then I'm going to divide by 20. That 20 is an exact number. There's no uncertainty. I know how to count to 20, okay? So you would not want to let that limit you, okay? Likewise, things that are by definition, okay? So I think later on in the notes we have one where there's 12 inches in a foot, okay? There's no uncertainty in that. Oh, is it really actually like, 12.1 or something? No, it's by definition. A foot is when you have 12 inches, lined up, okay? That might not, the quantity, how many feet in a meter, okay? That one is going to be one where that had to be actually measured and seen. And so, there are values probably out there if you Google that have different levels of significant figures, and you would have to adhere to that, okay? Because there is uncertainty in how many feet are in a meter to some degree. It had to be measured and determined. It's not a definition, okay? So that's the idea of exact figures. Don't let those limit you when you're doing these. Okay, and I'll put some text behind that as well. Okay. Okay, so, sorry. I'm sure you figured out that I have horrible handwriting by now, but I'm really working hard on trying to make it better. Exact numbers, okay? Do not limit SFs in calculations, in calcs. Okay. And not very inventive here. I have the exact same example I just mentioned. Calculating the weight of 22 people. Okay, I actually did one here, or I probably made it up. I don't think I asked a class what all their weights were. And And so 2,875.4 pounds, okay, divided by 22. All right. This has 1, 2, 3, 4, 5 sig figs. Okay, so our answer can only have 5 sig figs. We don't even consider this because it's an exact number. Okay, so what we come up with is 130.70 LES as our average. Okay. Okay, I have some practice problems for you to do to get more comfortable with sig figs. And I'll write them out. I suggest you pause the video and then do them. I won't pause. I'll give you the answers. Provide, actually this is just evaluating how many sig figs there are. And then I'll do some operations. Provide the number of SFs, SF again is sig figs, in the following numbers. Okay. 0.0. 1, 2, 3. I mean, this is A as in the number A. Okay. You know, I taught you scientific notation. Doesn't mean you're always going to have, you know, it's not a hard and fast rule. You have to use scientific notation, though it is quite handy. And here is one in scientific notation, 3.4, 0 times 10 to the third milliliters. Okay. C is 1.6402 grams. Okay. D 1.020 liters. Okay. All right. Pause. Try it. Okay. So that is 2 sig figs. Okay, that is 3 sig figs. Okay, trailing 0, if there's a decimal point, trailing 0 is significant. Okay, that's just a 0 in between, so they're all significant. So that is 5 SF. Okay. Yeah, I should have made the point up here. These leading zeros were not significant. Only 2 sig figs there. Okay, and then that's 4 SF. Okay. All right. So now some operations real quick. Shucks. Okay, I'm so sorry. This was supposed to be just called practice problems. And then this was number 1. Okay. And then perform following operations. Using, adhering would be a better word, but using adhering to sig fig rules. Okay. Okay, so 10.3 times 0.01345. Okay. B, to sort of exemplify the difference between them, 10.3 plus, same number, 0.01345. Okay? Give it a pause, figure it out. All done. Okay, so this is multiplication. It's going to be guided by the total number of sig figs. Total number of sig figs here is 3. That's 4. Okay, those guys are insignificant. So our answer can only have 3. All right, so our answer is 0.139. Okay. And in this one, it's guided by which one has the least number of digits to the right of the decimal place, and that is going to be this guy. There's only one digit to the right of the decimal place, so our answer can only have that. And so notice, our answer is 10.3. Okay. Had you added that stuff, and then tried to round, so, you know, if you add it directly, this is going to be 10.31345, okay? According to significant figures, you need to round to the nearest tens digit, rounds down, number stays unchanged. Okay. Okay. The next thing we're going to talk about, and that's the last thing of chapter 1, is something called dimensional analysis. This is one of my favorite things. Pretty nerdy. And I have a story that I wanted to relate. I always relate about this subject. This is incredibly helpful, dimensional analysis, and really makes your life easier doing calculations from here on out. And when I was a little kid in 5th grade, I think it was times tables. My 5th grade teacher, and I was kind of an airhead kid, and kind of a space cadet, not really like, oh, you know, who knows what I was thinking about. Probably baseball, butterflies, who knows. But I didn't pay attention very much at all. And then my teacher, Mr. Brown, said, if you don't listen to anything else I tell you this year, listen to this now. You need to know this. I think this was times table, although 5th grade seems really late for times table. Shoot, be a better story. Maybe I didn't listen all that well after all. In any case, at the time, I kind of sat up straight. Oh, this sounds scary. Okay, Mr. Brown, I'm with you. I'm with you. Go for it. Times tables or whatever the heck it was. And I listened and so forth and so on. That's what dimensional analysis is. Lock into this, practice it, use it, and it will make your life easier. Not only in this class, but if you go on to organic chemistry, biochemistry, so forth and so on. It will. It makes long calculations involving lots of different types of units much easier. Okay. A little bit of a hard one. You know, I always like to try to explain things off the cuff and then reiterate it on the board and stuff. It's a little bit of a hard subject to explain off the cuff. It's all sort of based around the idea that, you know, and this is again the example that I'm going to use on the board. If you have, you know that 12 inches equals 1 foot, okay? You could write that out as an equation. 12 inches equals 1 foot, okay? Now, if you, just think of the math, okay? 12 inches equals 1 foot. If I divide both sides by 12 inches, okay, I'm now going to have 1 foot over 12 inches, 12 inches over 12 inches. Well, that's just 1, okay? So what that means is that 12 inches over 1 foot, I screwed that up. I should just be doing this on the board. See, it's not that good of a... In any case, let me stick with it and try to take it home. 1 foot over 12 inches equals 1. Okay? Now, you can multiply anything you want by 1 and you don't change the value. It's a legal thing. Anytime you feel like it, do it. Okay? What that means is you can actually multiply anything by the quotient of 1 foot over 12 inches. And you won't have changed anything. Okay? And what does that enable you to do? Well, if you wanted to cancel out some units in a value that you already have here and transform it into other units, if you wanted to cancel out, you know, feet, or you wanted to cancel out inches, you multiply by that thing, and if it's on the numerator here and the denominator there, they cancel out, okay? And notice, by the way, that quotient I made, that 1 foot over 12 inches is 1. So is the reciprocal. 12 inches over 1 foot is 1, okay? So that's going to help you to do calculations. Probably not very clear how that's going to help you right now. But it will, trust me. What the heck else? And I think I've already mentioned it in this class. This always happens when I'm teaching the lab class. I don't remember if I said it in lab or I said it here, but a physicist once told me, and a very brilliant physicist from Princeton once told me that, well, Gideon, if you're trying to do physics, yeah, it's hard. If the units work out in the problem, you probably did it right. Okay, so that's definitely exemplified here when you're looking at dimensional analysis. Okay. Conversion, and I'm going to introduce this in a problem that's really just focused on converting units. Okay, so, but you can use it beyond. You can use dimensional analysis beyond only converting units. Okay, conversion of units. Okay, dimensional analysis. All right. Okay. So efficient way to convert units, do complex calculations. And we always introduce it with some fairly simple calculations. You might be like, I don't really need that. If you lock into it, then when you do some really hairy calculations, it'll make your life a lot easier. Okay, and again, this is sort of the validating the technique, if you will. Can always multiply by 1. Doesn't change value. That's the international symbol for change. Okay. And this is the basic validation of process. All right. I have an example. Multiply some number by 1, you get the same number. I think you guys are comfortable with that. Okay, so B. I'm not sure if this is the best way to describe it, but it's here on the paper, so I'm going to put it on here. Conversions. Set up as 1. Okay. So example, same one I discussed. 1 foot equals 12 inch. Okay, by definition. All right. Can rearrange. So 1 foot over 12 inches equals 1. Okay, simply just divided both sides by 12. And we can divide both sides by 1 foot. Okay, so 12 inches over 1 foot equals 1. Which means you can multiply anything you want by those. Now you have to adhere to the rules of units, okay? Units, a unit here that's on the numerator, a unit here that's on the denominator, those can cancel. If you don't have that situation where they cancel, then your answer has to keep those units. Okay. Multiply any value by the above without changing. That's a triangle, changing. Okay? Now, why would you want to do that? Well, you'd want to do that because it was canceling out units. Okay, you wouldn't just do that to do that. All right, let's do show with an example here. Say you have a piece of wood. It is 126.4 inches. Okay. How many feet? Okay. You don't need dimensional analysis to do this problem. You already know how to do that. Okay, but let me introduce this subject with dimensional analysis, and then we'll move on to harder problems to really show why it's useful. Okay, so the DA, dimensional analysis approach to answering this. I always like titles or labels for the calculation you're going to show here. Do that in all your work. It will help you, and it will help the grader give you partial credit if needs be. Length in feet. Okay. 126.4 inches. Okay. 1 foot is 12 inches. Okay. All right. Any units that are on the numerator in 1, the denominator in 1 can cancel. These cancel. Okay. You're left with foot. That was what I left with feet. That's what I was trying to get. So I know I did the problem right. Okay. And so that's going to be 10.53 feet. Okay. Notice, by the way, that I did not let the fact that there's just 2 digits here influence my significant figures. This is a definition. Okay. There's no uncertainty in that. All right. Okay, so let me do some more complex examples. I'm going to do some involving density. That'll be helpful for those of you in the lab who are doing a density lab. When I get the board too wet, then it's all funky. I think I just did that. Oops. Okay. All right. Examples. Involving density. Okay. 1.2 gallons of seawater. Okay. How many grams is this? Okay. Okay, so density of seawater. Notice that's going to be very different from the density of regular water. There's things dissolved in seawater. The density of seawater is 1.025 grams per milliliter. Okay? If you look at the back of your textbook, you'll see that 1 gallon is 3.7854 liters. Okay? So, you know, again, you could probably work through this problem, no problem, without any training in dimensional analysis, but a little bit more involved, a little bit more thinking, and you probably do it in multiple operations, and anytime you introduce multiple operations where there could have been a more streamlined single type operation, okay, you're probably doing the same ultimate operations, but whether they're separated or not. But the more separated they are, the more places you introduce to make an error. Okay. All right. So, general strategy I think about when I do these types of calculations is think about what you're after. Okay. Concentrate on what you're after. What are we after here? We're after number of grams. Okay. And start with what you know. Okay. We know 1.2 gallons. Okay. All right, so confirm what you're after, make your first value the value you know. Okay, so we're after grams of seawater. Okay. All right, well, we know that, oh, I'm sorry. Thought that was too few sig figs. That should have been a 1.25. Sorry about that, guys. 1.25 gallons. Okay. You can almost think now, we know our answer isn't supposed to have gallons, so we know we want to get rid of gallons. That's almost a trick you can use. I don't know, maybe that's what I'm always doing, but that's a trick you can use to get rid of the unit gallons, because we're looking for grams here. Okay. Well, so we know that, so I can take this equivalence here, okay, and I can either put gallons over liters or I can put liters over gallons. So I want gallons on the denominator, so I get rid of gallons. So 1 gallon, okay, is 3.7854 liters. Okay. At this point in the calculation, if I were to do it, the gallons cancel out. This is going to be liters. Right? I've now accomplished figuring out how many liters of seawater that is. All right. Well, the next thing I want to do is, trying to get to grams and stuff, but that's in milliliters. So first I got to deal with this liter to milliliter conversion. Okay. And again, that's a definition. I know that 1 liter is 1,000 milliliters. Okay? I should have done this before, maybe. So gallons cancel out each other. All right? Liters cancel out each other. At this point in the calculation, this all generates the number of milliliters in my 1.25 gallons. Okay? So now all I need to do is multiply by this density provided. Okay? And so that is 1.025 grams per 1 milliliter. Or milliliters. Okay? Milliliters cancel, milliliters cancel. All my units cancel out except for grams. That's what I was after. According to Steve Kaufman from Princeton, I should have the correct answer. Okay? And that's going to come up to 4.66 times 10 to the 3 grams. Okay? How did I come up with 3 sig figs there? Well, I'm doing multiplication here. This actually only has 1 sig fig here and 1 sig fig here because there's no decimal place there. But it's a definition. There's no uncertainty in that. Okay, so this can't limit our sig fig in our product. That can, and that can. That has 5 sig figs. That has 4 sig figs. That has 3. So our answer can only have 3. Okay? Okay, cool. I've got one more practice problem to do, and then we have accomplished chapter 1. It's supposed to be not how many kilograms is in 1 barrel, do you spell barrel, of crude oil? Okay. Some information you would need to answer this problem. 1 barrel is 159 liters. Okay. Now our density, okay, is 915 kilograms per cubic meter. Okay. All right. Definitely getting to a trickier problem if you're not using dimensional analysis. Okay. Okay. One thing that you would be helpful to remember. Okay, we've got 2 pretty different volume measurements. We've got cubic meters and we've got liters. Okay, I'm sure you can go on the internet and look up how many liters in a cubic meter. Okay, this is an exam. Let's say you don't have the internet at your disposal, so you need to work through this problem, and you can, no problem actually. Okay, and you can do that. Let me switch colors here. Remember, 1 liter is 1,000 milliliters. Okay. What is the value we remember? The convenient value that we remember for a milliliter. 1 milliliter equals a cc. Right? Yeah, give me 10 cc's of this, Dad. Like in a hospital. A cc is a cubic meter. Cubic centimeter, sorry. Okay? Alright, so we're starting to get close. Okay? How many cubic centimeters in a cubic meter? You're going to need to know that here. That might be a little bit tricky, but there's sort of a nice systematic way you could approach that. Okay. You know that 1 centimeter, okay, is 1 times 10 to the negative 2 meters. Okay, by definition, centi. If you look back at that chart that we made for our prefixes, centi is negative 2 to the power times 10 to the negative 2. Okay? It's 1/100th of a meter. Okay. Well, if you want to know how many cubic centimeters are in a cubic meter, you simply raise each of these, each side, to the power of 3. Okay, totally legal move. You haven't changed the equivalency there. Okay. And don't forget that when you have an exponent raised to an exponent, you multiply it. Okay, so 1 cubic centimeter equals 1 times 10 to the negative 6 cubic meters. Okay? All right, now we can set this problem up. Okay, start here with my title or my calculation label. What are we after? We're after kilograms of oil in a barrel. Okay? What's the quantity that we're starting with? And, you know, in a lot of these problems, there's no single way to do it. I should mention that. You can start with from multiple different places. Okay, but we know that we're starting with one barrel. I'm going to start with 159 liters. Okay, so I'm going to make this smaller so it can hopefully fit on here. I don't know. We'll see. 159 liters. Okay. And we know that 1 liter is 1.0 times, involving scientific notation here for you. 1 times 10 to the third milliliters. Okay. Those dudes cancel out. I know I am now at milliliters. Okay. And I know that 1 milliliter is a cubic centimeter. Okay, how did I know? Oh, why did you put the cubic centimeter up on the numerator and you put the milliliter down there? Well, if for no other reason I decided to do that because I knew that I wanted milliliters, I want milliliters in my final answer, so I got to get rid of milliliters, so I need to cancel them, and this is the place to cancel them. Okay, I'm now at cubic centimeters. I know my relationship between cubic centimeters and cubic meters. 1 cubic centimeter is 1 times 10 to the negative 6 cubic meters. Okay? Centimeters. And then finally, I can use that density that I was given, and that is 915 kilograms per 1 cubic meter. Cubic meter, all the units are gone except kilograms. That's what I was after. Lo and behold, we've gotten there. All right? That is going to equal 145.485. This is when my calculator kicks out. Now we got to make a decision about sig figs. Okay? That's an exact definition. That's an exact definition. That's an exact definition. So I'm limited only by these two guys. Okay? And that is a limiting factor. Okay? Yeah. That's a little bit weird. The 1 isn't a limiting factor, but that is a limiting factor. Okay? I'm blanking on a good way to explain why that is, but hopefully you see that. I mean, to figure out how many kilograms were in a cubic meter, that had to be measured for crude oil. It had to be measured very carefully. You know, depending on how carefully they did that is what determined how carefully, what quality of value you get for the density. Okay. All right. So in any case, 3 sig figs. It's multiplication. Total sig figs is what matters. Okay, and so we end up with, we round to the nearest ones place. Okay, it's 4, so we round down, 145 kilograms. That's your first chapter in Gen Chem. Congratulations. Hopefully hopefully things are a little bit smoother than the first lectures and stuff like that, and it will keep getting better and better. Okay guys, let me know if you have questions.